This is part one of a two-part episode on milling a mold half. In this episode, I'm going to be focusing on using adaptive and rest machining to cut out the cavity. And rest machining is really cool. Welcome to another episode. The more I use Fusion 360, the more I love it. And the community is fabulous. For this episode, I'm using adaptive machining. That's something new to me. I didn't have it in the CAM program I was using before. And it's really great because it controls the amount of load on the cutter. But the really cool thing is rest machining. And rest machining is cool because it looks at the material that was not removed in the previous operation, but now can be removed because you're using a smaller cutter. And that means that I can use smaller and smaller cutters, and I don't have to spend a lot of time cutting where there is no material anymore, which is something I had to do before. Now, about the community, there are some things that were not clear to me. So I posted a question on the Autodesk forum, and I was just blown away and amazed by how quickly I got a response and how good the responses were. This is just fabulous. The first operation is drilling pilot holes for the dowel pins. This allows room for 1/8 inch cutter to come in with adaptive milling to open up the dowel pin holes so that they're just slightly smaller than needed for the dowel pins. And later I'll come in with a reamer to drill it to the final size. This is supposed to mill out the holes for the dowel pins, but as you're about to see, I had the machine in the wrong position. I didn't know how far the mill had gone, so that means I didn't know whether I damaged the mold or not. But it doesn't hurt to finish the mold, because it's always possible to repair a mold. In this video, I'm going to focus on cutting out this part of the mold, as well as some of these tabs. I'm doing that with 5 steps. The first 3 steps are all adaptive clearing, and I'm dropping down in terms of tool size. So I start with a 1/8 inch end mill, go down to 1/16, and then 1/32. And doing that allows me to remove material in additional passes that didn't get removed by the first pass. So for example, here you can see that it's not able to mill into this area with a 1/8 inch end mill, but it is able to get into that area with a 1/16 inch end mill. The other thing that I'm doing with these three passes is after the first one I'm using rest machining. So it's only machining the areas where there's still material that has to be removed and can be removed by the smaller cutter. The final two steps are I'm clearing up the bottom and then clearing up the walls. Now the walls are interesting. I can't do that in a single pass because of the draft angle that I have on here. If you'll recall from the first episode where I designed the mold, I have a 5-degree draft on those angles to make it easier to get the parts out of the mold. And that means you can't do 2D milling, you have to do 3D milling to get that angle. Additionally, I'm using flat end cutters. I don't have any rounded end cutters, just ball nose. But flat is what I need to use for the walls. I have ordered some Lakeshore carbide cutters that have a slight radius on the end, so it's not completely flat. And I think those will do a better job. We'll find out in a future video. Going back to the 1/8 inch, which I'm going to show next, pretty much everything that I set up is the way I've done it in the past. So I set it to the feeds and speeds that I showed in the previous video. And then in terms of what I chose, I used a rectangle around the large cavity and then just clicked on these planes here to select those. And then the final thing that is relevant is I left 5/1000 both on the sides and the bottom. And that 5/1000 of an inch will be cleaned up by these last two passes here. Let's head to the mill and take a look. You can see that it's spending a lot of time cutting here. This is pretty easy to fix. You just have to lower the clearance plane. Here it doesn't really matter because there aren't that many entry points, but for the next cutting operation it does matter, and you'll see I'll change that. My compressor just kicked in and it's actually shaking the floor a little bit because I have it pretty close to the tripod. I'm using the compressor for a little blast of air to clear the chips out of the pocket, and it does a really great job. Now let's take a look at the 1/16 inch cutting to remove material where we couldn't get it out of with the 1/8 inch cutter. The trick here is something that wasn't obvious to me. I had to ask a question on the Autodesk forum, and I got an answer, which was a great answer. So let me explain what I was doing, which is probably what some of you are used to doing. When selecting the geometry, I was used to using stock contours. So you're probably used to clicking on stock contours and then selecting something like that, which controls the area that will be used for machining. The problem is when you're using rest machining like this, rest machining is creating a 3D model of the material that has been removed so far. So basically the milled operation, the material after the previous milling operation, and then it's using that to calculate the tool path. That means that when you select rest machining and stock contours, it's going to ignore the stock contours and create a tool path that covers the entire area. That's not what I wanted. So the trick is, instead of using the stock contours, you want to use geometry. Here what I did is I changed the machining boundary to selection, as you can see there. I selected the same rectangle that I used before, and that told it to keep all of the operations within that rectangle. So now it's able to calculate which parts of the stock can be removed with a smaller cutter only within that rectangle, and that's exactly what I wanted. If we go back and look at other settings, I left it with a higher RPM, which is what it came up with from the tool library. Most of the other settings I used similar values, so for example feed per tooth. And then for things such as optimal load, I continued to use the same expression, which is to use 10% of the tool diameter. So I pretty much didn't change much, and that gave me this operation here, which is perfect. Let's head to the machine and see how that worked. I'm a little bit nervous about this. This is I haven't tried adaptive milling with 1/16 inch cutters, so let's see what happens. I'm going to cross my fingers. Okay, I think you get the idea. Next up is 1/32 inch cutter to get rid of even more material, because there are still some places that the 1/16 inch cutter could not get to. So I follow the same strategy, which is to use the machining boundary instead of the stock contours. Pretty much everything else the same, and head it off to the machine and you can see what happens next. So what went wrong? Let's take a look. As I mentioned before, I used pretty much the same settings that I was using with the 1/16 inch cutter, but the 1/32 inch cutter is a lot weaker. And I was too aggressive on the step down. If you take a look here, I had the step down set to tool diameter divided by 2, which means for a 1/32 inch cutter, that comes out to about 16 thousandths of an inch. That was way too aggressive. So what I did for finishing off this pass with the 1/32 cutter is I changed it to tool diameter divided by 6, which I think is about 5 thousandths of an inch. And then this takes a while to calculate, but the end result is that it was a lot less aggressive. Unfortunately, it meant that it wasn't using much of the length of the cutter. I had been trying to use more of the length of the cutter, as suggested by John Saunders, for the adaptive milling, but that obviously didn't work in this case. Anyway, changing it to the diameter divided by 6 worked perfectly, and I was able to finish the cut. Now let's take a look at the finishing of the bottom. Here what I did is I used horizontal roughing, or horizontal finishing. I'm sorry, so it's this one right here, or just horizontal. And there's not too much I changed. I selected the same rectangle I've been using before. And then the important thing is in stock to leave, I set the axial to 0, which means it will mill all the way down to the bottom. And then I set the radial to 3 thousandths because I'm going to let the next operation take off the final material from the walls. And that's pretty much what I set. That gave me this result here. And as you'll see next, it did a great job cutting the flat areas, which include the bottom as well as some of these other areas that you can see here. The final operation for this episode is cutting the walls that have a 5-degree draft angle. So in order to get a reasonably smooth finish, I have a bunch of lines. You can see the step down is fairly small. This is done using contour, which you can see here, right there. So the contour is following a water line, where the water line goes down a little bit each time. Let's take a look at how I did that. Pretty much the same, selecting the rectangle. And then the changes in the step down. So if you look at maximum step down, I changed the, well, I didn't use an expression in this case. I set it to be 5/1000ths of an inch. And then the final thing that I did is I set the axial stock to leave at 1/1000ths, and I did this so that I wouldn't recut anything from the bottom of the cavity that was already taken care of in the previous pass. And then I set the radial to 0 so that we'll remove all the remaining stock from the walls. That's pretty much all there is to it. I'm not going to show video of that operation because it's pretty boring to watch. And next time, in the next video, we're going to focus on the runner system. And that was certainly interesting in and of itself. Thanks for watching. Please subscribe and see you next time.